The proton is one of the smallest particles in nature, yet it has a surprisingly large presence in the molecular sciences, meaning physics, chemistry, and biology. And this makes it one of the most studied of the naturally occurring stable particles. Now, what is a proton? A proton is just the nucleus of a hydrogen atom. It's what's left over when you strip away hydrogen's single electron. Interesting, however, the proton is not itself a fundamental particle. Rather, it's a composite particle consisting of 3 quarks, so 2 up quarks and 1 down quark. And this substructure makes the proton a particularly interesting particle to high-energy physicists who have a keen interest in taking beams of protons, of particle accelerators, colliding them together and seeing what comes out of the collisions. In so doing, they can test some of the most fundamental theories of the structure of matter, such as the Standard Model. Now, to chemists and biologists, usually the substructure of the proton is not what's interesting. They view it as kind of a fundamental object. They're more interested in how protons distribute themselves in complex chemical and biological environments. Now, in our basic chemistry courses, we learned that one of the ways to quantify how many protons there are is through something called the pH. The pH is just the negative of the logarithm of the proton concentration, and we learned that a value of pH of 7 is what's called pH neutral. In other words, that's the pH of liquid water. So a pH having a value less than 7 refers to an acidic environment, and a pH value greater than 7 refers to an acidic environment. And the pH of many subsystems in biology is a very important number. For example, the pH of blood needs to be a value just above 7, and it's the same for the pH of the environment of the brain, whereas the pH of the stomach, being very acidic, has to have a pH considerably lower than 7. Now, biology, of course, has evolved very clever ways of maintaining these pHs at stable values, as this is really necessary for life to exist at all. Now, coming back to acids, chemically, many acids have an extra proton to give up to the environment. And they do this usually by transferring that proton to the surrounding solvent, which may be water or whatever it is. And, then that gives rise to a finite concentration, and then that determines the value of the pH. In biology, there's actually been some speculation that lipid membranes, or the things that surround our cells, are held in place or stabilized by the presence of protons that come in through the surrounding liquid environment into the head group region, and they get trapped there, and they stabilize the interaction between these head groups, and therefore sort of provide a glue that holds these things together. But this is speculation that's still being tested. Now, in emerging clean energy technologies, we're also interested in the distribution of protons and pH values. We're also interested in how protons move, in other words, how they're transported through the system. So for example, a fuel cell, the way it works is there's a fuel like hydrogen that comes into one of the electrodes, the anode side, and it gets stripped of its electrons there, and so what's left over is protons. The electrons are then used to create an electric current, and that runs whatever device you want. And then the protons should not be allowed to build up at the anode, but they have to be transported through the cell from the anode to the cathode side, where they combine with oxygen to form water, which is just the waste product of the fuel cell. And how these protons are transported and how efficiently they can be transported through the system determines how well the fuel cell runs. The way the protons are transported is via something called a proton conductor, which is usually some sort of medium that can carry the protons from one place to another. A very typical proton conductor is water. All right, there are other media that can work, but water is one of the best known proton conductors that we have, provided there are excess protons in the system. Now, whether you're interested in biological proton transport or proton transport for industrial processes, As I mentioned already, water is one of the key things that we use. And a basic picture of how protons are transported through water actually goes back several centuries to a paper in around 1805 by C.J.T. von Grotius. All right, so von Grotius was a German chemist who was looking at electrolyte solutions and how charge is transported through them. But in 1805, we have to remember that the atomic theory of Dalton was just coming out. And so von Grotius certainly didn't know what the structure of water was. But he had this ingenious idea that it might not actually be a single charge that's being transported, but rather some sort of complex that's migrating through the system as a kind of topological defect. All right? But the way he envisioned it, of course, can't possibly be right because he didn't know what the underlying structure of water was. So my group has been very interested in trying to understand this process, not only in water but in other media. And we're using a technique, a computational technique called first principles molecular dynamics. Now, in a molecular dynamics calculation, we do is we take the Newtonian equations of motion, so Newton's second law, the same laws of motion that govern the motions of planets around stars and galaxies, but also work surprisingly well at the molecular level, and we discretize them in time and we solve them on a computer. The key input to a molecular dynamics calculation is the interatomic forces. Now, in chemical environments where we're going to be making or breaking chemical bonds, as we would when we're looking at proton transport, these forces actually need to be sensitive to the changing chemical environment. And the only way that this can be done reliably is to use the electronic structures. In other words, we have to solve the quantum mechanical problem of the electron distribution. And from that solution, we can derive the interatomic forces. These are then fed into the molecular dynamics calculation, and we can generate proton trajectories this way. Unfortunately, that's not always such a good approximation because it assumes that the laws of classical mechanics are valid, and protons, being hydrogen nuclei, are very light. They're actually governed more by the laws of quantum mechanics. So we need to account for these quantum effects in our system. But we can actually do that within the first principles molecular dynamics framework using a technique called the Feynman path integral. This is a technique by Richard Feynman, which formulates the quantum mechanical problem of the proton distribution or any quantum mechanical distribution in such a way that it can be computed through our first principles molecular dynamics approach. Not only can we get the proton distribution this way, but we can also get approximate proton and quantum dynamics. So, as I said, we've been studying proton transport in water and other media. So let me talk a little bit about water first. Water, being H2O, has an interesting phenomenon of having a charge separation in it. Okay, so the protons in water, the hydrogens, have a slight positive charge, and the oxygen has a slight negative charge whose magnitude is about twice that, it's exactly twice that of the hydrogens. And so this charge separation creates a kind of interaction between water molecules. It's a weak interaction in which the positively charged proton is attracted to the negatively charged oxygen. And this is a very directional interaction. This is called a hydrogen bond. And the calculations show that any proton that attaches itself to a water molecule will move from that water molecule to another one through the hydrogen bond. So I may have mentioned earlier that when a proton is in water, it attaches itself to a water molecule, forming a water molecule with 3 protons around it. That gives it a positive charge. And this is called a hydronium ion. And in hydronium, the 3 protons, or the 3 H's, are actually chemically equivalent. So any one of the 3 can then be transported or transferred to a nearby water molecule to form a new hydronium. All right? And in fact, 2 out of 3 times it's a different one from the one that originally transferred to the water molecule to form the hydronium in the first place. What determines which of the 3 protons it is has to do with the number of hydrogen bonds surrounding the water molecule that will take up that extra proton. Normally, water molecules have 4 hydrogen bonds around them, so they donate 2 through each of the hydrogens, and then they accept 2 through the oxygens. But these hydrogen bonds have a finite lifetime, so they typically live between 1 and 2 picoseconds, a picosecond being 10 to the minus 12 seconds. Okay, so that's 1/1,000,000th of a second. And when that happens, you have a water molecule with one missing hydrogen bond. And so if that hydrogen bond is one of the ones on the oxygen, then you have a water molecule that looks topologically like a hydronium ion, and that's when that water molecule can take up one of the protons from a neighboring hydronium, if there happens to be one right next to it. And so we see that the process of proton transfer, and therefore overall proton transport through the system, relies on these changing hydrogen bond patterns. And in fact, this is something that occurs in many hydrogen-bonded media. And the actual microscopic details will change from medium to medium, all right? But this dance of hydrogen bonds is something which is kind of universal to proton transport in all hydrogen-bonded media, and our calculations reveal that. They also allow us to calculate things that could be observed in experiments, such as diffusivities, rates of proton transport, proton distributions, and things that allow us to validate these microscopic mechanisms that we're finding. Okay, so that process in which the protons sort of hop from one water molecule to another, and it's also, in each case, a different proton. This is what's called structural diffusion, and it's called that because what really is happening is it's not one proton that moves through the system, but actually a proton complex that moves through this network of hydrogen bonds through these individual proton transfer reactions from one molecule to another one. But in many systems, there's another component of proton transport, which is vehicular. That is when the proton-containing complex just moves naturally, diffusing through the system as it normally would. And in many cases, this vehicular component works in the opposite direction of the structural component. In other words, these things are not synergistic, but they work against each other. And that actually lowers the overall rate of proton diffusivity. So one of the key challenges when we're designing proton conductors that may be useful for electrochemical devices like fuel cells is to try to find media in which the vehicular and the structural diffusion component work synergistically. There's still no good solution to this problem, but if it could be solved, then that would be a major breakthrough in proton-conducting media, and it would solve one of the outstanding challenges. There are many of them, but it would solve one of the outstanding challenges in the design of robust proton conductors for fuel cell applications. Now, computation actually has a large role to play in this. All right, when you're designing these proton conductors experimentally, it's a kind of just intuition and guess, and then comes the laborious process of synthesizing the relevant system. So if computation is accurate enough to sort of point the way toward promising candidate systems, then one can direct the synthesis toward those types of systems. All right. But from the computational point of view, there are still outstanding challenges as well, which is that the calculations, while accurate, need to get more accurate, and they also need to get more efficient. All right. And we're talking about large systems here, and very expensive calculations. So we need to find ways to make our calculations both more efficient and be able to treat the large systems that we really want to be able to treat. And this is going to occur through a combination of novel algorithms and employing emerging hardware such as graphical processing units. So I hope I've made the case that the proton really is a fascinating particle. Its role in chemistry and biology is an extremely important one. And as we learn more and more about designing proton conducting systems and how to control protons, I think the kinds of applications that we can see, that we can actually exploit, based on what we know about how protons work, can really be limitless.